Yeah.
I see.
Okay.
So, so this is the brief outline of what I'll be trying to elucidate in this presentation. So first I'll be talking about the features of weighted ensemble simulation, followed by what the algorithm that WE follows, which is the Huber-Kim algorithm, followed by how the kinetic parameters are extracted from this method, the applications, so areas where this method has been used, and also the possible future work in developing and improving this method. So some of the features are that the weighted ensemble simulation is a rare event sampling method. It is used in molecular dynamics. It focuses more on the functional transitions and the metastable states. So an example of this is, so we have certain trajectories or certain systems which we call as walkers. So instead of hoping by running just one system across a significant period of computation time and hoping that it will cross the energy barrier, what we do is we take 4 or 5 replicas of the same trajectory and give it different random seeds, which is generally using the Langevin thermostat. So we give which uses a Gaussian random number function, and then according to the relative positions of the systems, we replicate or merge the trajectories to so that we can focus the computation time more on the functional transitions on the higher energy states, which are more probable to go past the energy barrier, rather than focusing on those states which would rather remain at the energy minima, which is a redundant simulation for us. So the most important feature is that it does not have any bias potential as the other resampling methods have, like Gaussian accelerated MD or metadynamics, etc. So it gives rise to the true kinetic parameters. So the kinetic parameters that we extract are, we can say that they're the actual or the true kinetic parameters. And the W simulation follows the Huber-Kim algorithm, which I'll be explaining in the subsequent slides. So there are some essential basic terminologies and points which I would like to explain before explaining the algorithm itself. So bins are regions into which the configuration space is divided. So generally, suppose if our configuration space is the free energy profile of the system, bins are basically dividing the regions into different bins. So dividing the whole free energy profile into different regions, which are called bins. And walkers are actually the set of trajectories which are simulated across the configuration space. So, so as I was talking about the multiple trajectories, so those trajectories are called walkers. And progress coordinates or the collective variables are those parameters or observables which represent how the system has progressed across the configuration space. And the walkers or the trajectories are assigned statistical or probabilistic weights, such that the total sum of the weights of all the walkers is always 1. And another important point is that the total computation time is divided equally between the walkers. So the meaning of this is that suppose instead of running one system or one trajectory for say 30 nanoseconds, we'll be using three replicas or 3 similar or identical trajectories, giving them random seeds using a relevant thermostat, and we'll be dividing that 30 nanoseconds computation time into 10 nanoseconds each, and then we'll be looking at how each of the trajectories have progressed. So the Huber-Kim algorithm follows 2 major alternating steps. One is that, so there are 2 steps. So WE is one part of the algorithm, which is point number 2. So the first point is that we actually simulate the walkers for an arbitrary interval for a given time. And then according to the positions of the walkers, we resample the trajectory statistically. So WE relies on stochastic dynamics to simulate the walkers. As I was talking about the Langevin thermostat, which assigns random seeds to each of the trajectories. And the resampling is performed such that the number of walkers in a bin is always fixed, which I'll be explaining in the figure in the next slide. And because there is something called a splitting and merging of walkers, which I'll be explaining, there is a source that is a source of correlative errors in this method. So this is an example of how the weighted ensemble simulation is actually performed. So initially we have in the left corner of the picture has only one system. So instead of running just that system for an extended period of time, what we do is we replicate it and assign it statistical weights of 50% each. That's the probability of the transition occurring. That is in the weights are indicative of that. So we have two initial trajectories and then we run the dynamics. So dynamics is the general MD simulation that we do in this case. And then after we see the progress, now we see that one of the walkers has actually reached a higher energy state, which is in bin 2. So in the previous slide, I said that each bin should have equal number of walkers. So our targeted number of walkers per bin is 2. So what we do is that we replicate we replicate the trajectory in bin 2 as well as bin 1, because initially they have only one walker in each bin. And so so on and so forth, we do the WE. So we do the splitting here, and then we again run the dynamics. We observe how the walkers are progressing. And according to that, we do the replicating and merging. So here, if you see the third picture on the upper half of the slide, there are 3 walkers in bin 1 and 1 walker in bin 2. So we split that 1 walker in bin 2 into 2, and we merge 2 of the walkers in bin 1 so that there are 2 walkers. So by doing this, we're ensuring that the computation time is equally divided between both the bins, and we are equally focusing on the higher energy states as we are focusing on the lower energy states for the relevant trajectories. So generally, generally what happens is that at higher energy states, splitting happens most of the time, and at lower energy states, merging happens, which means that the computation time is divided judiciously. So now I'll be talking about the kinetics, and I would like to talk about the types of distribution of the trajectories across the configuration space first. So when we simulate the systems for very large time, the configuration space can actually relax into two distributions. One is a non-equilibrium steady state, where there is steady addition and removal of the particles, energy, probability, and any other parameter that we are looking for. And equilibrium distributions are those distributions of the ensemble where there is no addition or removal of particles or energy. So with the kinetic, with regards to the kinetics, I'll be talking with respect to the equilibrium distribution. So so we are trying to, so in equilibrium distribution, suppose this is an equilibrium distribution that we have. We see that there are two distinct regions in the equilibrium ensemble, A and B. So the trajectories which are in A, we denote with alpha set of trajectories, and those trajectories which are in the B equilibrium ensemble, B region of the ensemble, we term it as the beta set of trajectories. So in equilibrium distributions, the kinetic parameters are estimated using the direct estimation of observables, where the kinetics of a system can be estimated using the bin-to-bin transition probabilities. So we essentially look at how much probability has flown from, has transferred from one of the bins, from one bin to another, and based on that, we calculate the kinetic parameters. So the important relation in estimating the parameters is the Hill relation, where we define a term called MFPT from A bin to B bin as P alpha upon the flux from A to B from the alpha trajectory. So MFPT is the mean first passage time, and the flux from A to B is the probability per unit time entering B from A. So B and A are bins. So we are looking at how much probabilistic weights have moved from A to B. P alpha is the probability of the alpha steady state. I had talked alpha steady state means those trajectories which are in the A region of the ensemble. alpha steady state, and it is normalized in such a way that P alpha plus P beta is equal to 1. So we are looking at the rate constant. So rate constant is essentially the inverse of MFPT. For non-equilibrium steady state distribution, since there is continuous inflow and outflow of particles and energy, we use something called as a non-Markovian matrix estimation, which is a matrix of matrices where the rate constants are estimated more in accordance with how the probability of transition is seen in Monte Carlo simulations. So weighted ensemble simulation as of now has been mainly used in bio-based applications. Initially, when Huber and Kim had proposed this particular algorithm, they were using it to study Brownian dynamics at University of Wisconsin-Madison. And what is seen is that WE is very efficient in generating complete pathways and trajectories, because we are letting the system go across the energy profile or the configuration space on its own, rather than biasing it towards moving. So we are so that the set of trajectories which are generated are complete, they're not incomplete. And which is why it has been seen that WE is applicable in a range of resolution scales, from atomistic, where we observe things like protein binding, to cellular model resolutions. So I've taken one example of how the spike opening of the COVID virus was studied using WE. So two progress coordinates were used. One is the difference in the center of mass of the spike core to the RBD, which is the receptor binding domain. And the second one is how the RBD is oriented from its up state to its down state. So that is measured using the root mean square deviation of the RBD. And it was seen that the simulations which were done using WE were very much in agreement to the observations from cryo-EM and manifold EM methods. So this is a representative of a picture of the COVID virus and how the progress coordinates were chosen. And so this is a video which shows how the WE trajectories were simulated and how they were compared with the observations from MEM. So future work. So one of the major challenges in WE is the binning scheme. So bins are basically the regions in which the configuration space is divided. And so the most important part of very important and integral part of WE is that the construction and spacing of bins will always affect the efficiency of the WE, because bins give us an idea of where the trajectories are exactly positioned. So there's no formal way of constructing the bins. So there is actually current research which is being done in optimizing the binning schemes. So one of the binning schemes which has been highly successful is the minimal adaptive binning scheme, which is abbreviated as MAB, where there are initially fixed number of bins are spaced equally between the boundary trajectories. So but basically the boundary trajectories are those trajectories which are at the highest and lowest point with respect to the progress coordinate. So which is at the the one which is which has the lowest progress coordinate and the one which has the highest progress coordinate are chosen as the ends, and we initially construct equally spaced bins according to a number that we want. And then after the initial dynamics is run, we use a function called Z, which is log of the probabilistic weight of a given trajectory minus the log of the summation of all the probabilities, which is denoted by sigma pj. So where j indicates the trajectories which are higher than that particular trajectory with respect to the progress coordinate. So bottleneck trajectories are those trajectories which have the function z as a maximum, so which have that function z maximized. So in this case, we can see that I don't.
Yeah, you can see the screen.
Yeah. So yeah, so here we can see that this particular trajectory has only one trajectory after it in the with respect to the progress coordinate, which means that the function z for this particular trajectory is maximized. So this is identified as a bottleneck trajectory. So after the identification of the bottleneck trajectories, the bins are repositioned in such a way that there are equally spaced bins between the boundary trajectories again, but also we ensure that the bottleneck trajectories are placed in different bins and are assigned to separate bins. So which means that the bottleneck trajectories and the boundary trajectories are all in different bins. So this helps in efficiently replicating or merging the trajectories inside the respective bins. So error analysis is another part where there is scope for improvement with respect to WE. So WE is a non-Markovian strategy, which means Markovian strategies or Markov models are those models which are history blind, which do not depend upon the historical information about a particular trajectories. But WE is a non-Markovian strategy, which means that WE actually cares about what happened to that system in the previous run or in the history. So when we see that there are there is splitting of walkers and there are merging of walkers. So when a single walker splits, the child walkers inherit the history of the parent walker, and when two walkers merge to come as a single walker, that single walker actually inherits the information or the history of its two parent walkers. So that is a major source of correlative errors in the weighted ensemble simulation, and there is a search for alternate merging or splitting strategies which can reduce those correlative errors. So these are some of the references which can be read to understand WE in greater detail. And thank you very much for coming. Thank you.
Thank you, Siddharth. I have a question. So while assigning the bins or the probabilities for the configurations, is it so you start with the initial structure, right? Which has some energy, which has some Boltzmann distribution. So are the probability values assigned according to the Boltzmann distribution, or is it
no, the probabilities are not according to the Boltzmann distribution as of now. So what is actually happening is that, suppose in this case we are starting with two equivalent trajectories. So each of the trajectory has a probability of 0.5, and
right.
After dynamics is done, we see that one of the trajectories has gone up in the energy profile. So while replicating, what happens is, when we are replicating that particular trajectory into two different trajectories which inherit the same properties of the parent walker, so the probability is split. So the 0.5 probability is split into 0.25 probability each.
Okay.
So the splitting, yeah. So in this case, a splitting is divided by 2. In case we have 3 walkers per bin, then if one walker splits into 3 walkers, then each will have a probability which is 1/3 of the parent walker's probability. So the same thing happens with the merging also.
Okay.
It's essentially the same as Brun-Rich-Straussen-Bluf sampling. Essentially, this is the idea of the Brun-Rich-Straussen-Bluf sampling of the merging and splitting.
Oh, I'm not familiar with
that is a technique going back to the 80s.
Oh, okay.
It's a Monte Carlo technique out of the 80s, which essentially goes exactly the same way. was particularly being developed for configurational bias Monte Carlo, where you again split and merge, particularly split, and then some of them die when they are dying out.
Oh, okay.
It was developed
Very similar.
Yeah, yes, but very, very similar.
Yeah.
Interesting. Can you talk a bit more on how not applying the bias potential or not requirement of bias potential helping this versus other techniques like umbrella sampling?
Yeah, so when you are applying a bias potential to the trajectories, you are actually forcing that particular trajectory to move in a certain direction that you want. So what happens with that is that you are actually losing out on several other trajectories which actually might be possible. So so there might be certain trajectories which are at the metastable or the lower energy states for some period of time, but later it might jump across the energy barriers. So with WE, what you're doing is that you're allowing the system to evolve on its own. So as you see that there are trajectories in the lower energy states which we are simulating by giving it equal computational time, and hoping and we are making, and we are simulating it in such a way that those trajectories themselves, after a certain period of time, according to how the system is defined, crosses or does not cross the energy barrier. So the set of trajectories that we get from WE and ensemble is complete. Whereas where the accelerated MD, where we use bias potentials, we do not get the complete set of trajectories. We only get those set of trajectories which are moving across the free energy profile because of the addition of the bias potential.
Right.
That might, okay, but if you use something like an umbrella sampling or adaptive ensemble potential, again, you would get the ones which cross both ways. And if you have a kind of a general bias, then you don't run into that issue. Essentially, if you do a general umbrella sampling or any kind of weighted histogram reweighting, essentially what you're doing here. Essentially, histogram reweighting is adapted to MD, what you're doing here.
Yeah, I guess here, like, we're altering, I mean, in the case of like adding a bias potential, then you're altering the kinetics of the system. So I think that is the main.
But you also alter the kinetics of the system here anyway. As soon as you split, as soon as you split two and you're generating a new, if you're generating a new random seed at that point, and at that point, your kinetics is unreliable. You're breaking the kinetics.
No, not exactly. We're splitting the probabilities and weights like in a statistically correct way. So
yeah, I fully agree with you. Your configurations are correct, but your kinetics is not. You're in the correct ensemble. You're fully obeying statistical thermodynamics. No question about it. But but if you have two daughters, they obviously are different at that point. So that means at most one can follow the complete dynamics according to the integrator as before. The other one has to have a break in the dynamics at that point. Otherwise, so therefore your kinetics is still not correct. It's closer to correct. But it's not correct. Your ensemble is correct, but your kinetics is not.
Wait. Can you explain that again? Like why?
Well, essentially, if you split, your own the correct kinetics means that you're following the integrator consistently, the same integrator.
Right.
If you make two daughters,
you're
breaking the integrator at that point.
I guess with the random seed.
So if anybody would write the statement that the kinetics is correct as a reviewer, I would hit you over the head. Literally.
But I mean, I agree. Like with the random, like by using different random seeds, we're breaking the rule that we should use the same integrator. But still, I think if you run the simulation long enough, you can get enough statistics.
As I said, your ensembles are correct. Your thermodynamics is perfectly correct. No question about that. But your long-term dynamics not necessarily. Your dynamics not necessarily.
Yeah. I mean, in order to really check, like, it would be ideal to compare it to like just a one conventional, I mean, like several conventional long MD simulation trajectories to see like if the dynamics that we're getting from like long conventional MD is the same as this, but yeah, but still we can get useful kinetic properties like rate constants.
I don't disagree, but
Yeah,
it's kind of depending kinetics on which time scale you're talking.
Okay.
The long time scale is probably fine, the short time scale is probably not.
No, short time scale is not, that's why we have to run it for long enough, to get reliable, thermodynamic and kinetic properties, right? Yeah. And
What are
correlations
the
exist anyway, so.
what are the typical timescales?
Typical timescales are in the order of, so each simulation is a short, is defined as a short simulation which runs for about 10 to
200.
10 to 100 nanoseconds.
Oh,
Picoseconds.
Yeah.
Oh,
So
yes,
10
very
to
short.
100 picoseconds.
Very short.
Very short.
Very short.
Okay, and the overall is like in the microsecond scale, or can it go till milliseconds?
So
The entire
I
time.
think milliseconds, as Shirley had spoken about in her last presentation, only one lab
For
had done.
DD-Shaw, it's
Yes.
not really reachable yet.
Yes.
Yeah.
So I think realistically at the moment, I think microsecond time scales are done.
Yeah.
Yeah, okay.
Like hundreds of microseconds, right? Or tens of microseconds.
Yes,
Tens to hundreds.
tens to hundreds.
Okay.
Depending on the system.
If you want to go millisecond, you probably have to do a cost-weight model for this.
Oh,
You
yeah.
live on a cost-weight model, then you can.
Of course.
Then you can do realistically milliseconds.
Oh, yeah, but atomic scale, it's,
No.
oh, no, yet.
Clearly not.
yeah. In the future, maybe with computing power. Any other questions? And we can't see the chat, so if you guys can actually speak up, that would be good.
Hey Siddharth, can you hear me?
Yes, I can hear you.
Yeah, nice presentations, and the animation was really very descriptive. So could you quickly go to the minimal adaptive winning scheme?
Yes.
Yeah.
So minimal adaptive binning scheme is one of the binning schemes which has been proposed by Professor Lilian Chong of University of Pittsburgh. So I'll explain it using the figure itself. So we are looking at the trajectories. We are looking at the trajectories which are the highest and lowest progress coordinates. So this trajectory is at the lowest progress coordinate, and this trajectory is at the highest progress coordinate.
So this is where I had my question. So before even you start doing any simulation, you have no prior information as to what configuration corresponds to your higher coordination coordinate, like higher progress coordinate, and what corresponds to your lower progress coordinate. So like in that case, how do you go about actually assigning the bins? Because you did say initially that the minimal adaptive binning scheme it works in such a way that you know your progress coordinates, what corresponds to the low and what corresponds to the high progress coordinates, and then you assign like equally spaced bins. But even before you start running any simulation, how do you know what configurations corresponds to whether it's high or low? Like, do you do a prior rough screening across the landscape, or like what happens here? What do you need to, before doing this, do you need to have prior information about the system?
Yeah, we generally need a prior information. So from the paper of Professor Chong, so they were working on simulating the NaCl systems. So they were looking at the distance between Na and Cl for running the simulations. So the initial system that they had made had a distance, I think, of about 20 or 22 angstrom, and I think the intended distance between Na and Cl is about 3 to 4 angstrom. So that was 3 to 4 angstrom. So their progress coordinate was the distance between Na and Cl ions. And since the initial system that they had made was the NS, which was yet to be simulated, the distance between NaCl was around 20 angstrom. So that was the highest progress coordinate, and the target distance between Na and Cl was 3 to 4 angstrom. So that is how they had divided. So using those two, they had divided the bins.
But this limits you, of course, to linear progress coordinates. What happens if your progress coordinate is branched? So you have an initial state and you have two potential final states.
Oh, yeah, then no. Yeah.
Because that is in many cases, that is the problem.
Yeah, yeah,
Particularly
yeah.
reactive systems, you have a branched progress coordinate.
Yeah, so here, like, yeah, we're assuming that like we'll just have like one product state that will correspond to some progress.
Okay,
coordinate.
so yeah, so.
Yeah.
Yeah, actually that was my next question. So could you also like talk a bit more on the bottleneck trajectory? Like
Yeah, so the bottleneck trajectories are those trajectories which have the function z, which is defined as log of pi. So pi is the probabilistic weight assigned to that particular, which that particular trajectory holds, minus the log of the summation of pj, where summation pj is the summation of all the probabilities which have a higher progress coordinate than the bottleneck trajectory. So if you see in the diagram, this particular trajectory has only one trajectory ahead of it, which means that sigma pj is actually just pj, where which is a probabilistic weight of this particular trajectory. So we can see that so the function z is maximized for this case. So that is how the bottleneck trajectories are identified. The physical significance of why that particular thing they're choosing, I'm not very sure, but it has been found little more efficient than keeping the bins constant during the whole configuration space, and adapting it according to this spacing of trajectories has proven to be more efficient in sampling out efficient trajectories efficiently.
So the log of the probability is because that effectively mimics a free energy.
Yeah. So by maximizing the objective function z, like that corresponds to the Walker or like bin that would have like the highest energy barrier. So that's why we're labeling that as the bottom.
So you want to spend essentially, you really want to focus on the top. You want to artificially spend more time at the top, because that's the hardest to sample.
Yeah.
So we want to distribute the computation time equally between the lower space and high space.
Exactly. Yeah. So yes, and the highest free energy space is the hardest to sample, because it's normally the lowest probability. So that's where you artificially focus.
So generally what happens is the configuration time is skewed between the highest and, because there are not many trajectories which are at the higher energy state.
Exactly. Yeah, sure. Clearly. Yeah, makes sense.
Any more questions?
Do people also run this backwards? What have people tried to kind of do run this backwards, start from the high energy state and see if you find back to the low to the correct low energy state?
Well, I guess I've mainly just used this to just make progress from the initial state to the reactant state, and I mean it's been able to like reach the product state a lot more quickly without
No, but if you start there to make sure that your algorithm is correct, to make sure that you actually find back to where you wanted to start.
Oh, I see. I mean, I guess I used it assuming that it's correct. I mean, I'm sure the paper has like check for its accuracy for simple systems, right? Like for NaCl. Yeah.
So it also the paper also shows that using the conventional binning scheme, the number of trajectories that were obtained were almost half that of the number of trajectories which were generated using the minimal adaptive binning.
So which way? You have more in the minimum binning or
Yes,
less?
we have more in the
Yeah,
middle.
okay.
More trajectories
Yeah.
are simulated, so
Mhm.
which covers the configuration space much better than the keeping the bins constant in the configuration space.
And do you run into the same issue like all these parallel tempering that the larger your system, the smaller the bins you have to make?
Mm.
Because the more bins you need.
Yeah, more
The
bins,
larger
yeah,
the system is, the more bins you need,
of
because
course,
then
yeah.
your energy distribution
Yeah.
becomes narrower.
Yeah, more, yeah,
Yes.
we need more bins, yeah.
So you have the same problem there. That would be nice to get around that one.
Yeah. Oh,
Yeah,
well.
I'm just curious how it was done with the RBD, the spike of COVID, RBD and the ACE2, I think, right?
Oh,
How was the binning done, like compared to NaCl system? Was it
Oh,
like,
okay,
because
I'll
spike
answer
is,
this because this was my paper, but I mean, for the spike system in that paper, it was before MAB came out, unfortunately, so we had to manually bin, and we had like these very fine bins like near the states that had like the free energy barriers, and bigger bins at like low energy, and it was very painful. But I mean, with MAB, like, I mean, I ran MAB on the same spike system and along with the variants, and it's a lot faster. Yeah, like I
right.
don't really care about the spacing anymore because this adapts it on its own. Yeah.
I say it's 2021, and I think your paper was 2020, right?
Oh no. Oh yeah, it got published in 2021. Yeah.
Okay.
Yeah. So I guess maybe right before this got published. Yeah.
Yeah.
Same year, but yeah.
So I'm just curious from a software implementation point of view, is the WE method, is it like a ready available plugin that we could use with any empty software, or does it just work with some specific software?
Currently, WE works with Amber.
Oh no,
No,
like
but
anything,
yeah, it can work with any. So people have used it on Amber.
Amber, GrowMax,
GrowMax,
OpenMM,
OpenMM,
like
yeah.
a lot of MD, yeah.
Like most of the papers which I had studied, people had used Amber because.
I guess, yeah. Yeah.
But
It can be used for other
the
things.
software which is Vespa weighted ensemble simulation and Vespa weighted ensemble simulation.
I always forget simulation toolkit and
Toolkit
analysis.
and parallelization analysis.
Yeah.
Vespa. So
Yeah.
that software, it's actually a Python package. So which you can import, which you can import and and it has a proper documentation in which you can design how you would like the W simulation to run.
So Professor Shirley, are you the kind of software developer, or is it like someone has developed?
This was mainly developed and maintained by Professor Lillian Chong's group at University of Pittsburgh. But there are a lot of other contributors like myself and other people who are working on
Okay.
like WESPA related algorithms.
Yeah, because like generally in catalysis community, I mean, like people don't really kind of do a classical MD simulation. But even if one wants to do, I think the most preferred software is generally LAMPS.
Oh yeah.
So I was just thinking other ideas like to release a plugin or something like that, so that people can just use it readily.
So I've actually been using WESPA with lamps with one of my collaborators who's working on platinum nanocrystals. And I mean, we're still working on the project, and I mean, we're a bit far away from writing the paper, but we'll definitely release the code like that we used. But I mean, it was pretty easy. And if you need it right now, then I mean, I can share the code as well. Yeah.
Okay.
Yeah.
So like I'm just kind of planning to do some kind of metadynamics in lamps. I just saw some plugins. So I was just like wondering, like, what about this? So, yeah.
You can still use the Wespa plugin, but I think it would be helpful to have like, so yeah, it's kind of hard to explain without actually like, for both of us to see the like how Wespa is structured, but basically as long as, yeah, I mean, I'll probably try to release like some sample, codes and scripts that can show like how we can use Wespa along with lamps. But I mean, it wasn't that difficult actually. You just need to,
Okay.
you just need the links to like lamps, and then replace like MD simulation execute commands like that are like in lamps or OpenNM or other MD. Like you can just replace that with the lamps execution command, and yeah, so it's just a matter of replacing, with lamps.
Okay.
Yeah, but if you need it, yeah, you can just email me and I can get.
Yeah, I will kind of follow up with you at a later stage when I'm at that point.
Okay.
But yeah, that's good to know. Thanks.
It sounds good. Yeah. Any questions? Oh, actually, yeah, maybe before we end the meeting, for the more senior graduate students. Oh yeah, for the more senior graduate students, can you guys give some comments about how appropriate like this this presentation is for Siddharth's like prelim? Because yeah, I don't know what's really goes on in the prelim examination. So
prelim is really focusing on existing, on papers.
Yeah.
So if you use this as one of the papers, then yes, this would make sense.
Oh yeah. It's like Siddharth basically presented about like 2 papers essentially.
Exactly. So that is really what the prelim is about. The prelim is really about presenting 2 papers, and then the one thing which for the prelim would be missing is the critical analysis.
Oh, okay.
Really not only reproducing it, but really critically analyzing kind of what is missing, what are the limitations, this kind of stuff, really the critical analysis piece. That would be missing from the for the prelim.
Okay, yeah, that makes sense. Do you guys have any additional thoughts?
What I always recommend before the prelim is kind of really do a prelim dry run, obviously.
Oh yeah.
Yeah.
I always say both for prelim and for qualifying exam, invite senior graduate students and make it harder than the actual exam. So that the people really ask the harder questions. So really make it, if the actual exam is easier for you, it's actually nicer. So yes, really the dry runs should be really hard and critical, that in the end it should be smooth sailing in the real exam.
What is the other paper that you're presenting?
So the other paper that I was planning on presenting was about the minimal adaptive binning scheme,
Which is this?
which is this, and the second paper, the first paper which I will be presenting is the review paper about this one, written by Professor Zuckerman and Professor Chong, about weighted ensemble in general, so which covers every aspect of right from introduction to kinetics to applications and possible corrections and future work.
I'm not sure if the paper will be given to you, right, Sudesh?
No, so I'm not sure like what is the procedure for this time around, but in general in chemical department, no, the papers the student needs to
Select.
choose for themselves.
Chemical engineering are different in that respect, I know.
Oh, okay.
In chemical science, you get the paper from the outside, completely independent. So the 2 departments are running that differently.
And also the committee was told to us at a kind of last minute. So like, so that I just think that probably you shouldn't keep it very method focused. Like, I mean, if it's 10 minutes, then it's a good idea for you to like split your talk into like, just say like, if you're going to do a review paper, then maybe like 5-6 minutes focusing what is there in the literature without getting very much into detail, just like brushing over things, and then leave the next 2-3 minutes to take an example that was published, and just focus on that and just highlight how weighted ensemble method is actually helping it, and then even maybe you can just in the future work or something like that, you can just put the minimal adaptive binning over there without getting into too much detail. Because one thing you need to remember is it's just 10 minutes, and they are generally very particular that you need to finish it exactly at 10 minutes. So you can't go beyond it with it. It really comes down with your chair, but most of the professors didn't prefer it during my cohort time. So if the idea is for you to finish your talk in 10 minutes, and also consider that you may have some experimental people. So if that is the case, then how do you really communicate what are you trying to say, right? So you don't really need to my advice to you would be probably don't focus too much on like very small subtle details. You can just give you a brief overview. Like just think about if you're going to teach this to your grad as an intro class, what will you say without getting into too much detail? Like
Yes.
that would be my biggest advice to you.
Yeah, and also would say, don't show too many formulas in the actual prelim, but have them ready if they come up. So and whatever is on the slide is absolutely fair game to be asked about. And of course, you can play the game to put on purpose things on the slide which you don't talk about, then you will guaranteed ask about that.
Yeah. Yeah, but keep them handy so you can use the equations on the board while explaining. So that helped me a lot.
Yes.
I didn't display a lot of equations, but when they asked questions, I could just write down the equation and say, this is what is happening.
I'll keep those things in mind.
And practice well. Timing is very important. And I think this presentation was really good. Yeah. Keep the time in mind and keep practicing.
Yes, I'll do that.
And one more thing is like make sure that you don't throw some jargons while speaking, because often questions get formed just from that. So just like when you were presenting, I just saw like you were using some Markovian, non-Markovian models and stuff like that. So people get intrigued and then they'll ask you some questions. And you also somewhere I think where you're comparing and contrasting metadynamics and other methods, you did say some Gaussian distribution. So the simple question is like, can you just go to the board and write a Gaussian distribution formula or something like that? So you need to anticipate these kind of questions.
I would disagree that Markovian is jargon, because that is stuff we talk about in StatLab.
Well, Professor, it's kind of still a jargon for me.
It's still a jargon for him. Yeah, that's what he said.
But it is standard class. It's standard comes up in thermo class, and whatever comes up in a regular class is not jargon.
Okay.
So jargon is only field specific, but a Markov process is not jargon anymore. That is for a grad thermo class, that is standard.
I guess if all the first years have taken your classes. I guess.
Yeah, exactly. Yes.
Okay. Yeah. Okay. So I think with that let's thank Siddharth one more time. And thanks for asking questions, giving comments, and see you guys next week. Bye.
All right.